All right. Exciting conclusion of Unit 2.12, 2-12, whatever you want to call it, logarithmic function manipulation. We finished up the last lesson by, well, we talked about change of base, but specifically what we were doing was we were showing that horizontal dilations can be manipulated to look like vertical shifts, which is pretty neat. And I kind of let the cat out of the bag earlier in the lesson, not today, obviously, in the last lesson, and I showed you how change of base could be used to treat a base change of a logarithm actually as a vertical dilation. We're going to see that happen in the notes today. One time, but at least it does happen in the notes today. Something else that we're going to see happen. Using this exponent property that says that you can bring the exponent out of the argument position and down to the front. If you bring this thing down to the front as a multiplier, you have a dilation on your hands. Remember, because multiplying by a number on the front of something is always going to be a vertical dilation. And we don't care if it's a stretch or a shrink. We just care that it's a dilation, okay? I do need to caution you, though, for questions like this one. If this wasn't here, and again, there should be parentheses here. Anyway, if this wasn't here and you put this on Desmos, this is a two-sided graph. You could substitute any x value you want, positive or negative, because squaring it is going to give you a positive number. The only x value you can't use is, boop, 0. And that's because, well, 0 squared is still 0. And the argument of a logarithm must be positive. So 0 would be the only no-no for this function. However, if we're saying the function is just this, we are not allowed to take this exponent out of the exponent position of the argument and bring it to the front. The reason why is because x could have been negative. And if you'd done that, then you'd say, you know, number in front of logarithm with negative argument, big time not allowed. So in order to use that property, we always have to restrict our domain. In fact, if we come back, it was sneakily done. Look at right there. If m and n are positive, then these rules hold true. So it was already there. We just didn't really make a big deal of it. Alrighty. So for this first one, it says use the power property to show that this is actually a dilation of this as long as x is greater than 0. Easy peasy. Because our power property says any exponent of the argument can be brought down to the front of the logarithm, giving us our g of, let me switch colors, giving us our g of x as 2 log base 2 of x. That is a vertical dilation, factor 2. We'll graph it in just a second. Part C says describe the change in output values over equal length input values. That literally just means describe the transformation. So you say vertical dilation, factor 2. If you wanted to make a rule, you could. You can show that every x comma y on f of x is going to map onto an x comma vertical outside same, right? So you see a 2 on the front, multiply those y values by 2. You also could have just written, double the y values or multiply the y values by 2. Anything like that would have been the description. This is the rule. Now, let us graph f of x. I'll graph it as a blue function. Log base 2 of x. Log base b of 1 is always 0, so log base 2 of 1 is 0, so I have the coordinate 1, 0 on the parent function. Log base b of b always has a value of 1, so log base 2 of 2 has a y value of 1. And then from there, we need our argument to just be powers of the base. So the next one would be 4. Log base 2 of 4 is 2, log base 2 of 8 is 3, so on and so forth. Connect your dots. I've been practicing my log curve skills. I'm lying, but it looks like it. Now, let us graph g of x. And instead of actually plotting points, I'm just going to use the transformational rule that says, hey, just double this thing's y values. So this y value is 0. It doubles to remain 0. How about that? This y value is 1. It doubles to 2. This y value is 2. It doubles to 4. This y value is 3. It doubles to 6, which is technically on the picture. Now, I do want you to see this point. I happen to have plotted it perfectly. That is at 1/2 comma negative 1. And that should make sense because 2 to the negative 1 gets me 1/2. So there it is. If I double that y value, it puts me here. Because negative 1 times 2 is negative 2. The reason why I did that is because I wanted you to see this. Everywhere to the left of that x-intercept, the blue function f of x is greater than the green function g of x. Because anytime you double one of these blue y values that's negative, it becomes more negative. So blue is always greater than green to the left. However, to the right, because you're doubling, green is always greater than blue. I just wanted you to know that they're never going to intersect ever again. There it is. Pretty easy, right? Okay, great. This next question makes no sense the way it's written, so we're going to edit it so that way it makes more sense for us, and it'll just be a straight up and down better question. We're going to say that g of x is log base 2 of x. And we're going to say that f of x is log of x. The goal here is to show that log base 2 of x is a vertical dilation of log of x, the common log. This one would be log base 10. And this is us using change of base to demonstrate that. And it wouldn't matter if we used the natural log of x or the log of x. It's completely up to you. We could use log base 3 of x. It doesn't matter as long as the logarithm that we choose on the top and bottom have the same base. Doesn't matter at all. But since this says log, I'm going to go ahead and use the common log. And the reason why I'm choosing to use the common log is because I altered this to also be the common log. That's why. This is base 10. Okay, so let's take our g of x, which we know to be log base 2 of x. I'm going to use change of base, and I'm going to use the common log. So I'm going to write this as log of x divided by log of 2. Now, log of 2 is a number. I don't know what power I have to raise 10 to get the number 2, but I do know it's less than 1. I do know it's more than 0. So it's somewhere between 0 and 1, because 10 to the 0 would have been 1, and this is a 2. Okay? But it's a number. That means I can write it like this. It's like saying x over 2 is the same as saying 1/2 times x. And I'm going to grab a calculator, and I want to figure out what log of 2 equals. Oh, look, a number between 0 and 1. 1 divided by that number, and no, I didn't need to do it in 2 steps. I could have just done 1 divided by log of 0, or log of 2. Is he going to drool on my wall? Jack W is using my wall as a pillow back there with his mouth wide open. He's going to drool on my wall. Don't you know? I've taught regular students in this room. For all you know, they licked that wall. I knew you weren't licking the wall. I'm just saying. What'd you say? Okay, you're not wrong. Let me get closer to the mic. What she said was I'm talking about regular students like they're animals. And I said she's not wrong. Anyway, so what we just found out was that this is about 3.322. There it is. Oh, look, a vertical dilation of log of x. How about that? Before I graph them, I do want to go ahead and write the rule again. And the description would be vertical dilation, factor, and you could write about 3.322, or you could just write 1 over log 2. Boom. So all of our y values are going to just be a little bit more than triple what they were before. Isn't that neat? Changing the base of the logarithm is actually a vertical stretch. So cool. Man, I'm nerdy. Okay, let's do orange and blue. So we'll have f of x be orange. This is log of x, and I can barely make this work. Log base 10 of 1 is 0 because log base b of 1 is always 0. The next thing you want to do is get an argument equal to the base, which is 10. So log base 10 of 10 would be equal to 1, which does barely fit. Okay? Now I'm going to do my best to make this a very steep log graph. I have to turn the paper actually. Why does it look so bad? Yours or mine? Oh, because you're not used to drawing logarithms. Don't beat yourself up. Rather than plot the points of log base 2 of x, like I did in the last one in blue, what I want to do is I want to take these orange coordinates and do my best to multiply them by 3.322. Okay? And we'll do that in blue. So this one, if you multiply 0 by 3.322, you get 0 back. And this one is 1, and 1 times 3.322 is just a hair bigger than 3. So like here-ish, that feels like 3 1/3-ish. And now I'm going to do my best to draw a curve through those two. That was pretty good. Perfect? No. Pretty good? Yeah, actually. Actually. Uh-oh. Let's see how good I am. Log base 2 of 2 is 1. Almost perfect. Log base 2 of 4 is 2. Almost perfect. And log base 2 of 8 is 3. Almost perfect. So as you can see, yes, multiplying by 3.322 to the common log will just about get you log base 2 of x. How about that? So neat. So that is your one example of demonstrating that changing the base can actually be written as a vertical dilation. Cool beans? Okay, one person's with me. Fantastic. Alrighty, moving over to the back side. And on the back, we are literally just graphing and analyzing the functions. So this is more like just reviewing what we've already talked about. In order to find the domain of a logarithm, we must make sure that the argument remains positive. So we say x plus 1 had better be greater than 0. Subtracting 1 from both sides gets me this. So a domain of -1 to positive infinity. Infinity? Yeah, there's two t's in that word, infinity. Now, because it's a logarithm, I know it has a vertical asymptote, and because my domain begins at -1 without including it, I know that that is actually the asymptote. X equals -1. Like that. So I know my domain. I know the range because the range of all logarithms is the same. All real numbers. So we're going to say from -infinity to positive infinity. This graph is shifted left by 1 unit from the parent natural log. Yes, there's also a reflection and a stretch, but those are both y changes. This is the only x change. So what that is going to do is it's going to affect my x-intercept. Log base e of 1 would have been right here because we would have had log base b of 1, but it's been shifted to the left 1 by that. So it's actually here now. That means I know my x and y intercepts. They're both 0, 0. You don't need to find a y-intercept, bless you, unless you're specifically asked to find a y-intercept of a logarithm. And if you're going to do that, just use x equals 0. Okay, it's usually not going to be pretty. This one happens to be pretty, but it usually won't be for logarithms. Time to graph it. That makes it upside down. That makes it tall. It gets close to this line, goes through this dot. I'm just going to do my best. Since it's a natural log, I can't plot any more pretty points. So we're just going to get close to the asymptote. Remember, it's upside down. So it does that. And I don't know, it does something like this. Good enough. It's just a sketch. That's good enough. So if we want to discuss this thing's behavior and its concavity, what two descriptors could I give it? This is concave up. That's one of its two descriptors. So I'll write that. Hold on. Let's give a, what is it? Decreasing. That's the other descriptor. Good. So it's a decreasing curve that is concave up. And now all we have to do is write its in behavior using limits. Unfortunately, it cannot go to the left forever because it's going to be stopped by a vertical asymptote at -1. But we are on the right side of that asymptote. Boop. And at that straight line, my graph is going to get really close to it and is going to shoot straight up without bound to positive infinity. Nothing gets in the way as I go to the right. But the graph is decreasing, so it's going to be approaching negative infinity. Boom. There it is. So like I said, it's just a review of the other stuff that we did. Pretty darn easy. Yeah, I'm just waiting. I still see pencils scribbling. Pens and pencils are moving, so I'm waiting for people to catch up. Alrighty, last example. Just like before, this argument has a square on it, which means the domain of this function is actually every single number except for the one number that makes the argument 0, and that would be x equals 3. However, we're going to go ahead and restrict our domain to numbers less than 3 because we want to be able to use transformations to graph it rather than just trying to big brain our way through the natural log of something squared. So we can actually change this to, since we're restricting, to natural log of 3 minus x. We know the domain. It was actually dictated. The domain had better be less than 3, so we're going to say from negative infinity up to positive 3, meaning we also know our vertical asymptote. Since all logarithms have the same range, we can go ahead and fill that information in as well. Awesome. Let's talk about what kind of transformations we see here. What we know is the number in front of our x is negative. That means our graph points to the negative x's. The number in front is positive. So we know this graph points up and to the left. It's going to get close to this asymptote, so it's going to go wee like that. In order to get a more accurate graph, since it is a natural log, the only pretty point that we can find will be its x-intercept. And the x-intercept is found when y is 0. And the only time you can get a logarithm have a value of 0 is if its argument equals 1. Just reminding you of the special rule. So we need to figure out what makes our argument equal 1. We already know what makes the argument equal 0. That's where the asymptote is. 3 minus x is equal to 1 because we're trying to force this y value. Clearly, x is 2. So this thing is going to cross through the x-axis at positive 2. And then it points up and to the left. So again, because it's a natural log, it's never going to be pretty except for that one time. So I'm just going to, sure, that felt like a natural log. Oh, we found its intercept. We need two descriptors for this thing. Using first difference, what could we say? This is also a decreasing function like the first one was. And using second differences, what could we say about it? Concave down. Awesome. Then all that's left is limit behavior, and we could put a bow on this lesson. As x heads to the left, nothing is ever going to get in its way. And this graph will go up without bound. But as we head to the right, our asymptote at x equals 3 will get in the way. We're on the left side of it though, so it's 3 negative. And that's when the graph is going to crash down. And like I said, we put a bow on it, nerds.